Hello, welcome to my session. My name is Emil Kotrc. I work for Broadcom, and I will be talking about joins. The session is cross-platform, but I work mostly for DB2 for ZOS. So please bear in mind that many things I will mention here are platform-specific. Most of the topics are really cross-platform, but there are some differences. So please keep that in mind if you're working with different platforms. I have very busy slides. I have about more than 80 slides, so let's go directly to the slide deck. Here is my agenda. So I'll start with a very brief history, where this started, and then I speak briefly about the types of joins. Most of developers know this already, so I will go very quickly through that. And then I will jump into some interesting stuff, which is not very well known about some other joins, Antijoin, lateral join, and such. I will also mention some tricks. We'll speak about implementation of joins because I think that's an important topic to understand how the joins are working in DB2. So we'll speak about join methods and how predicates are being evaluated by DB2. And at the end, very briefly, some performance considerations so that developers can understand how DB2 may transform some queries into joins, how it can manipulate the predicates and such. The reason why I did this session, or why I was preparing that, is that I learned that some of the developers do not fully understand the joins. They kind of know the concept, but still they are not very clear on some of the stuff. Some of the experiences they get from some older implementations or some other database management systems. So they are currently not up to date. Many developers still do joins in the application, so they select from different tables and they do application types of joins, which is not the most efficient way in many cases. So that's why I wanted to make some introductory session to the joins. Where this started, so I need to give credit to all these experts I list on this slide. So many things I have in these slides is a compilation of what I learned from the experts. So thank you for that. I really appreciate the IDUG because that's where I was learning the stuff. But it also contains some of my content. I wrote some articles about some stuff which is also included here. But really the many things I learned from the experts. Unfortunately, I don't have all the links because there are so many. I have some links at the end. But if you see some sessions from these guys, I think that you know them very well, and that their sessions are really good and go technical and deeply into details. So thank you. So let's start with the history. So where this all started, I'm pretty sure you have heard about Mr. Kotrc, who created this relational model in IBM in 60s, early 70s, I believe. So and he wrote this article called Relational Model of Data for Large Shared Data Banks. And in a paragraph I list here, there is a mention about joins. So this is where this started, or this is the first material I found. So maybe there are some even prior works, possibly, not sure. But this is where I learned about the basics of the joins. And really it's based on relational algebra. So all is math basically, and some math operations, how to do these joins. So this is just a reference for you if you are interested into the history where this started. So this is the first reference I found. The next slide just lists some basic definitions, but I will skip most of it because I'm pretty sure that at least you are aware. So basically the join is an operation that combines columns from two or more tables and creates a join tables. It doesn't have to necessarily be just two tables, but can be two or more tables. And they don't have to be distinct, which means that I can even join the same table to itself. You need a join condition which specifies the pairing of those tables and some join operators. So the join operation retrieves the joined columns from two or more tables and creates a row. Retrieval is based on some specified condition, which is the join condition, and join type defines how the rows are formed if there is no match. Some other definitions, because the tables in the join are sometimes called composite, inner, outer, new. So that's what I list here. We also speak about null supplying table, which is in case of outer joins. In case of left outer join, it's the right table. In case of right outer join, it's the left table, and it's both tables in a full outer join. And the other table is usually called the driver table, which is the table that is returning the data. Just a simple visualization. So we have table 1 and table 2, and we do join on the blank. So that's our on the white space. So this is our join condition, and we just join the green and red columns. Again, some basic definitions here. On the left, we have the composite or the left table. We join it with the right or new table. Then we create this composite or new left table, and we join with the new right table, and we have the result. So in this case, we do the two join operations. So this is really just about the definitions. Type of joins. Again, pretty quickly, the types of joins are defined by the ANSI standard, and there are three main types. Cross, which is basically a cross product of the tables. Inner, which is cross product, but keeping only rows where the join condition is true or when the join condition is met. And then we have outer joins, which includes even the rows that were missing from the other table. We have three flavors of the outer joins: left, right, and full. I will show them in a moment. And then I also want to speak about some other types of joins, which are in fact one of those prior kinds, but they are in a special category in my slide. So I will speak about the anti-join, which really just joins the rows from the left table, which are for which there are no rows from the right table. I will speak about the Equijoin, natural join, self-join, and lateral join. So the cross join is basically really the cross product of the two tables, if I join these two tables. So what is important here, the number of rows is really multiplication of, or the product of the number of rows of table 1 and table 2. There are two syntaxes available. The older one just use in the from clause to specify a comma b, or the newer syntax where you use the explicit cross join syntax. So, and this is an example again. So we join these two tables on the blank column. Oh, sorry. In this case, we join those green, and so we have for the green we have two rows from the right table, and the same for the blue. So there is no join condition in this case. Inner join. In this case, we must have the join condition or join predicate. So it's kind of a cross product where we only keep the rows where the join condition is true. So for inner join, order of the tables doesn't matter, and the same for the predicates. Again, there are two syntaxes available: the old one, which has the join condition, the where clause, or the new one, which has the special join clause in the syntax. So simple chart. Here we are joining on the orange, so we just get one row back. Example, SQL 86 and SQL 92 syntax. So the first one, join condition again is in the where clause. In the second, at the bottom, you see we have this explicit join condition, or it can be even explicitly inner join condition. What's important here is that how does it work with filtering? In this case, it doesn't matter for inner join. It doesn't matter if you have the filtering in the join clause or in the where clause, and that's kind of obvious because in the old syntax you don't have any other choice anyway. So that is how it is working. So in this case, we have this join condition. We want to join on department number, but we only want to see departments that start with D. In this case, even if we use the old syntax or the new syntax, results are the same. Keep this in mind because later I will speak about the outer joins, and that's where this produces different results. So you need to keep in mind. For inner joins, all good. Outer join was introduced in DB2.4. There were some prior workarounds I have found using union and not exist clauses and such. But since DB2.4, it's easy. We have this outer join. Can be 3 flavors, left, right, or full. The results can include the data from rows that have unmatching values as well as the matching. So now the only available is the new syntax. So you need to explicitly code the join condition using the join clause. And order of the tables is very important here. So it really matters. And the filtering predicates must be part of the where clause. I will show you an example in a minute. So here is a nice diagram which I grabbed from the IBM documentation. So you can see the source at the bottom, so which clearly shows how it works. So you have the left, full, or right join, and you see those nulls from the null supplying table. So in the case of the left outer join, the null values are coming from the right table. So the values are coming from the left, and the nulls are supplied from the right, opposite from the right outer join. And for full outer join, we have nulls on both sides. Simple diagram using these diagrams, but I hope all is clear here. So left outer join. So the driver table is on the left side, and the null supplying table is on the right side. If the condition is met, DB2 will return the rows from the data from both tables. If the condition is not met, DB2 will supply the null values from the right table. So in our case, we have the department table is on the left, the employee table is on the right. Very similar thing for the right outer join, just the tables are swapped. So the driver table is on the right side, the null supplying table is on the left side. So there is no performance difference between the left and right, and in fact, at least DB2.4z treats both these types as a left join. So if you do an explain of the right join, you will see it transform to the left join because it's really the same thing. It's just the matter of the syntax. Sometimes it helps for the readability to use right join rather than left join, but internally it really doesn't matter. Full outer join is different because the driver and null supplying tables are on both sides, in fact. So you see the syntax is using full outer join here, or in short, full join. And I'm just matching on the employee number and manager number. Okay, so that was a quick walkthrough on those types. Now the important thing is how you do filtering on outer joins. As I mentioned for the inner joins, it doesn't matter if you have the filtering predicate on the where or on the join, but now it really matters. And if you want to do filtering, you have to have the predicates on the where clause. So let's say we have this example where we want to join. We do the left join from the department table and employee, and we only want to see the rows from the departments that start with D. So on top, you see how the example how it should look like. So we have the join condition in the on clause, and we have the filtering on the where. Now, what happens if you change it and remove the where clause and add the filtering predicate into the on clause? The thing is that now you don't filter the data, but you just specify a different join condition. Now the join condition is only in case that the department number is equal to the work department of the employee, and the department starts with D. So in these cases, we will do the join, and for others, we will just supply the null values. So let's take a look. So for the first case, if the where clause is present, so we have, okay, that's what we would expect. So we have only departments that start with D, and we join them with the employee table. For the first department, there is no employee, so that's why we see the nulls. But for the others, we see even the employees. But if you take a look at the second output, you see different results, right? So we see all departments basically, because he didn't provide any filtering. That was the only join condition that we provided. And the join condition was only for tables that started with D. So as you can see, we only have D11, D21 that contain some employee. I think it was a manager maybe. And for the rest, we just have nulls. So we don't do the join, we don't filter. And that's the point. So again, in the second example, we don't do any filtering. We just have a different join condition. So how the join condition looks like. So this is a screenshot from the documentation. For inner left or outer join, right outer joins, it can be any stage condition. For full outer join, can be only equal predicates combined with and. Now let's talk about some different types of joins. Self-join. As I mentioned at the beginning, the join doesn't necessarily need to join two distinct tables. So you can even join the same table to itself. And there are many use cases why you want to do it. For example, you have a foreign key, a self-referencing foreign key in this table. Example is the department table, which has also the administrative department, which is the department that's managing the departments, right? You can compare the two other rows in the same table, or you can even join a table multiple times in some cases. So let's take a look at some examples. If you have self-referencing foreign key, I mentioned the department table from the IBM sample tables. So you see there is the administrative department column. So when I just do a join with the department table itself to see for every department to see its administrative department. So the output will show me that. I can compare to other rows in the same table. Example here, I'm doing a join from the employee table to itself, and I just wanted to see, and I'm comparing the education level. So I want to see employees that have education level higher but lower salary, right? So that will help me to do this report. Other example here. So what we are doing here. So as you can see, we have 3 join conditions, and we are joining the employee table twice, and that's because for every department we want to see the manager, and for every project, I believe, we want to see the responsible employee for the project. Okay. So that's why we do join of the employee table twice. Equijoin, nothing special. It just uses the equal predicate, can be inner but also outer, no extra syntax, just really that's a term for the join if you have the equal predicates. Natural join, kind of interesting because I have seen this in some different types of database management systems, and then I learned that this was removed from the standard at later versions. So DB2 doesn't support this natural join, and which is kind of correct as I've learned, or as I heard, which is correct based on the latest standards. So it's a special type of the Equijoin, and it means that we are joining on tables that are equal on their common columns. So let's say you have, in our case, we have the department and project tables, which both have department number column. So if you have this natural join syntax, it would just join on those same column names. It's not supported by DB2, and as I said, that's based on the standard. However, you can still talk about this even for outer joins, and that's where it is used. For example, you see I'm doing the full outer join. So I forgot to say that even if it's not supported, I mean, let me go back, even if it's not supported on DB2, you can still do it, right? You just need to provide the explicit join condition. So it's not a big deal. So it's not that it doesn't work. It's just the syntax natural join is not supported, but you can do the join. You just need to specify the join condition, as you can see. So let me go here. So I do the very same thing, but I just do the full join. But I select all the columns. And what will happen is, in this case, I will see for the department number, I will see two columns. One is coming from the department and the second one from project. And there is this coalesce or value function that will allow me to just see one column. So you can see it on the box at the bottom that I'm using the coalesce for department number from the employee and project table. So I will see only one column. If you take a look at this example, so the first one is if I don't use the coalesce, so I see two depth number columns, and you see there are some nulls because I'm doing the full outer join. So at some point the driver is on the left and null supplying is on the right, and vice versa. But if you use the coalesce, I will see only those non-null values. Okay. Antijoin, interesting technique which can be used as an alternative to not in or not exist subqueries. And in some cases, it can perform better than subqueries, especially for large data. Again, if I say it performs better, you need to test it, verify in your case, because there is no best solution always. As you know, it always depends, so be careful. But what it is, so antijoin is basically an after join predicate in an outer join to filter data based upon the fact that the relationship between the two tables does not exist, which means that this antijoin is a predicate looking for those null values, right? Example on the next slide. So we are doing the same thing using three different techniques. So we are selecting employees who do not work in department that starts with D, right? So, and as you can see on the top, I have two subqueries, one correlated and the second non-correlated subquery, or vice versa in my case. Sorry, the first one is non-correlated, the second one is correlated. But at the bottom, you can see how I can use the antijoin. So I really do a join of employee and department table. So when I select, so I do the left join, right? And then, because I know that, and my join condition in this case, look at it carefully, the join condition has the department equal to work department and department like D. So which means that I am only doing the join condition on department that start with D. So, and I'm doing a left join. So the rest of departments will contain the nulls. So that's why I have this where condition where the deep depth name is null, which means those are those departments that don't start with D. So, and that's the trick. So really simple, but can be very powerful. Lateral join. And I'll start with example. So I had a chat with one of my friends, and he was like, hey, can you do this with DB2? So just simple example, show me all departments and 3 employees with the highest salary. So I just naively typed this SQL into Spoofy. So because like how you can select 3 employees with the highest salaries, that's the subquery there, like the select. And I had this reference to the departments, and I just fetch first 3 rows only, and voila, then I hit enter and I got this error, right? The reference is not valid in the context where it is used. So I was like thinking, whoa, what's going on? And then what I learned, I needed a very simple change to my query. Maybe you wouldn't even notice, but please notice the table keyword function before the subselect. So I'm now joining department plus the table of select, which I have there, which gives me the result I needed. And this construct is called lateral join. So this is the result if you are interested. So you see all those departments with the employees, with the 3 employees with the highest salaries. And this is what is called lateral join. So if you take a look into the documentation, by adding the table keyword, which is also known as the lateral correlation, DB2 allows a join of a table or a nested table expression, which can have a correlated reference to the previous table, not just a reference to table from a higher level. So if you let me go back, the point here is that my reference here, the work department equals to department number from the D table, from the department table, is referencing the table which is on the same level. So my from clause references the department table and then the subquery. So, and that's what lateral join helps me to do. So, and I then learned that this was available in DB2 for ZOS since DB2.6, which is 1998. And it's available in LUW, where it even allows the lateral keyword as a synonym to the table, right? And that's the point. Another join, semi-join, is similar to a natural join, but in fact the table is not joined, but only checked for a join condition. Kind of looks similar to this anti-join, but now we just check if the data exists, right? Or so I have a join of 2 tables. I have the equal predicate on the common column names, but I will only select data from the column 1 and from the table 1, and columns from the table 2 will not appear in the result. Example, and again, alternative technique. I want to see employees that work in a department, right? Because I might have some departments that don't have any employees. So how I can do it? I can do this on the left hand. I can use a subquery, right? And on the right hand, I can use a join, where I join all columns. So I will select all columns from the employee table, and I will join with the department table. And the condition is where the work that is a department number. So I will only see those employees that work in a department. Yeah, interesting stuff. I don't know if you are familiar with the column mask that were introduced. I believe it was version 10 for ZOS, not sure about LUW, but this is kind of thing that allows you to mask some data. And I had a discussion with one of my smart colleagues, and he was like saying, hey, what's the point? Because you can reveal the data using joins. So we had some discussion about it and come up with simple workaround how you can unmask the data. So let's say I'm creating this mask for the bonus table, which means that I want to hide the bonus if it's higher than 500. So I will just display null. So I will add this column mask to my table, and then if I do the select, I will see the bonus. If it's higher than 500, I will just see now. So I cannot see that. How you can see the secrets using the joins? Oh, pretty simple trick. So what I do here, I create this called hack. So you see, I do this table expression. So when I just generate numbers from 1 to up to 30,000 in my case. So that's in the with and union all, which is recursion, which generates just the numbers 1 to 30,000. And then I select from the employee table and I join it with my hex table where the bonus is equal to the number, and then I will just display the number from the hex table. So, and as you can see on the output, I still have my bonus nullified because the column must still apply, but I have a new column, unmasked bonus, where I can clearly see the bonus because of the join. So really be careful. I wrote an article about that you need to be careful when you are doing this column mask, because in some cases it might be easy to see the data. For some, definitely it will be more difficult than in this simple scenario, but still there is a way. So be careful with that. Okay, and that was the quick run through the types of joins. And now let's briefly take a look at the implementation of joins. So back to basic definitions. So we will speak about the composite, new table, left, right, and such. So here is an overview of join methods that are available in DB2. Nested loop join, merge scan, hash join, or hybrid join. And now it becomes more platform specific. So I will be mostly focusing on DB2-4Z, but we'll mention LUW as well. But I don't have much experience with that, so please excuse me some errors or mistakes. Nested loop join, a simple idea. DB2 scans the outer table, and for every qualifying row, it searches the matching row in a table, right? If no matching row is found, then for inner join, it just discards the row. For outer join, it concatenates the row with the null values. So, which means that the inner table is scanned repeatedly. So usually it is used when the outer table is small, so that DB2 can limit the number of loops for the inner table, or if you have some highly clustered indexes on the join column, so that it can take benefit of it. For DB2-4Z, DB2 can create so-called a sparse index on the inner table, which I think I have on the next slide. Yeah, the sparse index. So sparse index is an index pointing to a range of n contiguous rows other than a specific row, and it allows some hashing. This technique is kind of equivalent or to the hash join, which is not available in DB2-4Z OS. DB2 can also sort the outer table under certain condition, so especially if the index is fully clustered and so on. So this is the basic idea. So you scan the blue table, and for every qualifying row, you take a look into the yellow table, which is the right table on my diagram, and it goes like that. Merge scan, on the other hand, is different, and it goes through the tables in the same direction. It requires one or more equal predicates. DB2 scans both tables in order of the join columns, which can cause or imply some sort of the tables, or DB2 can use the proper index to do so. So that's the technique. If an unmatched row is found, it's discarded for inner join. For left, the data comes from the, if it's a left join and it comes from the inner table, kept if it's left join and it comes from the outer table, and is kept if we are doing the full outer join. When this is used, if you have one or more equipredicates, and usually when the data, the tables are big. So again, usually DB2 can use some indexes or even sort the data, and then goes from top to bottom on those tables. Hybrid join is kind of difficult. It's, I think, available only for DB2 for ZOS. I think I haven't heard about this one on LUW. There is an interesting article. I think I believe I have a reference at the links at the end of my session. The reasons behind that. I forgot the details, honestly, about the main reasons and such. But the point here is that DB2 it has two stages or two phases. And in the first phase, the DB2 joins the outer table with record IDs from index in the inner table. So it really requires to have an index for the inner table. And then it sorts the data and then uses the list prefetch to fetch the data from the inner table using the reads. So this is used especially if you have a non-clustered index. And I believe this is available only. Sorry, let me go back. Yeah, it's available only to inner joins, right? So it doesn't work for outer. So, and this is my visualization how it works. So on the yellow side of the chart, you see the table plus the index. So in the first phase, DB2 joins the reads plus the left table, and then it does the list prefetch and joins the data from the yellow table. Hash join, I believe this is only available for DB2LW, not for DB2-4Z. But for DB2-4Z, there is an alternate technique, the nested loop join with the sparse index and the hashing. So how does this work? So there is a build phase where DB2 reads the inner table and creates an in-memory hash table for qualified rows. And in the probe test, it reads the outer table, calculates the hash and finds the corresponding row. So this is it. So the green part is the hash calculate. Star join, honestly, I don't have any experience with that. Applies to a star schema. So we have this fact table and multiple tables, those dimension tables, and DB2 joins them. So kind of in some scenarios, this is used heavily. Requirement here is that there is a single index on the fact table that supports the filtering, and it's provided by the dimension tables. There is a similar technique which is called Pairwise Join, which requires independent or separate indexes for those fact tables. But as I said, no, unfortunately, I have no experience with that, so I will just let it to you, and maybe you can share your experience with that. All right, so that was about the techniques, how DB2 does it internally. I believe it's still important to understand, because if you do the explain, you can see different techniques. So I still believe that developers should know more about those things. What is more important, I think, though, is the developers also should understand how the join predicates work and what is the order of the execution of the predicates, because you can have a different types of predicates. Just an overview how this works. So in DB2-4Z, we have these layers like this relation data service, data manager, buffer manager, and such. So you get a request, and there are different services that handle your request and retrieve the data. Again, you have likely heard about the stage 1 and stage 2 predicate. So it's written here. So stage 1 are like cheaper, stage 2 are more expensive because you involve the higher level to do the calculations and filtering. So for join predicates, they can be simple or compound, local or join. Important thing here, Boolean term predicate. The recommendation is to use it as whenever you can, because in join operations, Boolean term predicate can reject rows at earlier stage than non-Boolean predicates. So, a definition of Boolean predicate is that the whole clause is evaluated false if a Boolean term is evaluated false. Again, take a look into the documentation, learn more about it. So here is just an example from the doc discussing what is the Boolean predicate. So the recommendation is use Boolean predicate as much as you can whenever possible. So what can be the predicates on the join clause? Let me quickly see what I wanted to say here. Yeah, so again, going back to my very first example, Join condition and filtering for inner join can be done in the on clause. For the outer joins, it's only the join condition, not a filtering. So this is really important to understand. I know I am repeating this many times, but I have seen some errors on that. The on clause was containing filtering, which didn't work. For full outer join, it can be only equal predicate. And in outer join predicate can be evaluated during the join, like stage 2. Predicate in a table expression can be evaluated before the join as stage 1. So the join sequence is not necessarily the same as the order in which the tables appear in the predicate, and the optimizer can reorder. If you see bad performance, you may even want to reorder. Again, at the bottom, example from the documentation, which lists like if in this case, if T2 is the first table in the join sequence, the predicate is stage 1. If T1 is the first table in the join, then the predicate is stage 2. However, DB2 is evolving over time, so these things are subject to change as well. So what about outer join predicates? So we can differentiate between different types, outer, during, and after. So before join predicates are predicates in the where clause, and they can be stage 1, and they provide some filtering. So even before DB2 will be doing the join, it can filter some rows out, so which will mean that it will work with less data. During means that predicates are included in the on clause and are evaluated during the join. And after, there can be two flavors of after join predicates. One is after the step, which is available since DB2.6, as I have learned, and totally after join. Predicates that again in the where clause, and they are applied after the join happens. And I have seen a very nice article from Terry Purcell about that. I have a link at the end of my session. So let's take a look at before join. In this case, it's really before, because DB2 will filter these rows out. So all the rows that are less or equal to 100 will be just left out, and they will not be joined. Right? There is no reason, because they will be filtered out. So this is a typical before join. This is a during join predicate because it's in the on clause. So you see the difference. In the prior example, it was in the where clause. Now it's in the on clause. So it's a during join because that's the join condition now, right? After join step predicate, in this case, we are having two join conditions. So, and this where clause can be applied after we join employee and department step, right? So before we do the second join, we can remove, or DB2 can remove some rows. So this is the after join step. And the last one is totally after join predicate, which can be done really after the join happens. And typically it's this antijoin or this, so that's the example here. So we just do two joins, department and employee, and then we join the employee project table. So, and this is really at the end because we need to do both joins before we see the result. So I believe this is important to understand that when you have the filtering, where you have the join predicate, and what is evaluated when, because then you can optimize a bit your query. The last section of my slide deck is about the join manipulations and transformations. Now, DB2, as I said, is evolving. So in some cases, it can do some optimizations on its own and some transformations even on its own. In some cases, you may help and you may even provide the alternate technique on your own rather than relying on DB2 doing that. So what can DB2 do? DB2 can modify predicates. It can add some extra predicates or even remove some. It can transform subqueries to joins. It can add extra predicates. It can transform full outer joins to left or right. Can change the left, right to inner joins. So different techniques. So you may code your SQL actually, and then if you do the explain, you may see a bit different technique being used. So that's why you need to be careful and understand what can happen. For example, I have here an example how the full outer join can be transformed to left outer join. As you can see on the left hand, I have full outer join, but DB2 can transform it to the left join. And what is the reason? The reason is the where clause, right? Because we say that the x from the data from the x must be higher than 12, so we don't have any nulls there. So similar to the right outer join to inner join, again, we are not supplying the nulls. So very similar thing here. DB2 can add some extra predicates. It's called transitive closure. So if we have column 1 equals column 2 and column 2 equals column 3, it means that column 1 has to equal column 3, right? On the left hand, you can see how it can be transformed and some predicates can be added. So they are highlighted, but it's not clearly visible. So you can see them in bold. Because we do the where clause is T1, column 1 equals to column 1 in both tables, and we want to have the column 1 in T1 greater than 10, which, by the way, means that even the column 1 in table 2 needs to be higher than 10. DB2 can even transform a subquery into a join, or you can do it on your own. And you know, it's not always the best practice, but I usually like to use the joins rather than the subqueries. And the reason why I try to do that is that DB2 usually has more options for evaluating joins. As you have learned, there are at least 3 techniques which DB2 can use for joins. It can use the nested loop join, merge scan, or the hybrid join. While in subqueries it's more limited. So, but DB2 evolved and it can do it even on its own. So in this case, you see that we are selecting employees from departments which are in San Jose or San Francisco and division in marketing. So we can do it using the subquery, or we can use the join here, as you can see. So, and in this case, it was non-correlated, right? Subquery that was transformed because there is no reference to the employee table. In this case, we have another example. So we have correlated subqueries. One is using the exists and the other one is using the in. So we are selecting employees who work as designers and are working on project MA 2100. So again, in this case, I can transform it to a join, or DB2 can do it. So this was just a quick some quick techniques that DB2 can use, so that you understand that, hey, even if I code my SQL this way, DB2 can still use the join, even in the case I was not thinking about that this can be transformed to a join. And this really concludes my session here. So I have some references, and if you like, really take a look at the doc I provide. So I have some references to some articles and some IDUG articles. I know that sometimes links do not work, so if you have difficulties to get to the data, let me know, and I usually have all the links downloaded, so I can provide it to you if you are interested. And I hope you enjoyed the session as I did during the preparation. I hope that it was quiet all here in my virtual my virtual office, because our babies are just next door, but I asked them to be quiet for a moment. So I think it worked well. So thank you very much for attending the session. If you have any questions or comments, I have my email address here, so I will be happy to reply to you if you have any questions. Please don't forget to fill out the session evaluation. Oh, well, but I don't recall if there is any session number. Hopefully it is. So, but in any case, if you have anything, let me know. I'm really happy to reply. Thank you very much and have a nice day.